Hi everyone, my name is Behruz and I'm a privacy engineer at Shopify. Today I'm going to share with you the story of a metamorphosis in our data analytics platform to facilitate privacy requests, in particular, how to make deleting the undeletable possible. Here's a bit about Shopify. We are a global commerce company with more than 1.7 million merchants of all sizes all around the globe. We have had more than $300 billion worth of sale on our platform. And in fact, last Black Friday, we hit more than $1.5 million sales per minute. So as you can imagine, there's a lot going on this platform. And we collect a lot of analytical events to improve our own platform and help our merchants with their decision making. This is a general overview of how our analytical platform used to look like in the past. So there was a lot of events getting fired from across our platform. They would go through our messaging pipeline and get persisted into our data warehouse, where our data analysts could use them for their analysis. So you may be wondering, why am I telling you about this? And it has to do if you take a closer look inside our data warehouse. It turns out this event oftentimes contained personally identifiable information, or PII for short, and we needed a way to be able to efficiently find and act on PII in our data warehouse. And this quickly escalated to a very difficult task because, first of all, our data warehouse was designed to be immutable by nature. So once the data entered, it would be very hard to delete or edit it without disturbing downstream jobs. Hence why we call it the undeletable. Second, historically, these events were collected in an ad hoc manner and they lacked any guaranteed structure. So it made it really difficult to understand what is PII or where is PII. Third, even if we knew or could find PII in this petabyte scale data warehouse, it was still hard to relate it back to a data subject. So we could find an IP address within petabytes of information, but it would be really hard and require a lot of tedious work to understand who is the data subject for this specific IP address. The fourth factor was missing dependency graph, and this could potentially introduce cascading failures should any change or deletion happen in any of these data sets and disrupt our production systems or dashboards. And last but not least was volume and scale, both in terms of the volume of data and in terms of number of people who depended on these data sets. There were hundreds of data scientists who use this data set in their day-to-day job, and anything that we were going to do was and needed to be very scalable and consider that fact. And it wasn't also privacy or these issues. There was a lot of other costs, maintainability, and reusability issues that were related to these data sets as well. So it kind of brought up a natural opportunity for us, the privacy team, and the data team to address this problem together and collaborate. The rest of this talk, I'm going to tell you about our collaboration and how we address these challenges. So in our first step, we started with context collection. And we did so because we thought missing context was the root cause of a lot of problems that we were facing. Our first step was to introduce a schematization system. Schemas are proposed by developers or data scientists who are interested in capturing new events. You can see an example of an event schema on the right side for the sign-up event. Let's read through this schema and see what kind of context it collects. First, we have structure. So every field within the schema has a guaranteed data type and no more binary cryptic blocks anymore. And if this event change over time, we capture their evolution context via our versioning system. And last and most importantly is the privacy context that captures first the data controllership, who is the controller, who is the data subject, and what is PII within this event. You can see the email and IP address are marked as PII, and we also have these handlers that are called privacy handlers that define what to do with PII. So more on this later. So we talk about schemas and context collection, but we still haven't figured out how to address our original goal of deletion. To do so, we decided to not allow or have any PII in our data warehouse. So this kind of sounds counterintuitive, and that's because if we remove all PII, then we lose analytical value, and our data scientists won't be able to do their job. So to address this, we use what GDPR calls pseudonymization. Pseudonymization is processing of personal data in a manner that personal data can no longer be attributed to a specific data subject without use of additional information. In particular, we use two types of obfuscation, two types of pseudonymization, obfuscation and tokenization. In obfuscation, identifying bits of data are masked, and it's an irreversible operation. So for example, if you have an IP address, it gets half masked. Or if you have a user agent, all the specific parts like resolution, clock skew, or font are removed. But we don't stop at the obfuscation. We enrich this with high-level non-personal data as well. So for example, if you have an IP address, we geolocate it. If you have a user agent, we extract the operating system or device from it. And it turns out this actually addresses most of our use cases, and our data scientists are very happy with them. But there remains cases that data scientists require the access to the raw value of PII, and that's where tokenization comes into the game. So in tokenization, we exchange the raw value of PII with a consistent randomly generated token. And we store the mapping in a separate service. So this consistency is a key property, and that allows our data scientists to use the same tokens to track a certain individual without accessing actually their raw PII. It's also worthwhile to mention that pseudonymization and data that has gone through pseudonymization is not same as redaction, and the data that has gone through it remains personal information as long as there is a way, directly or indirectly, to relate it back to a data subject. But it allows for control of personal data and reducing the risk and being able to anonymize and remove when needed. So this was a lot to process. Let's see how this makes sense in an example. Here we have an example of a sign-up event, and we built this tool called Scrubber that applies pseudonymization around our events, and you can see the scrub format of this event on the right side. So we had an IP address that got half masked and also geolocated. And we have an email address that got half masked its local part and also tokenized. So every other time that we see the same email on the same circumstances, we're going to give the same token. And this is that consistency property that I talked about earlier. So let's take a step back again and see how all of this schematization and pseudonymization helps us with our goal. So if you take a closer look in our data warehouse, we kind of end up with three categories of data now. So it's either non-personal data, things like ID, timestamp, or it's obfuscated data with high-level information, or it's tokenized data. So if you have a privacy request, for example, deletion, we don't have to do much for the first two categories of this data because there's not anything personal there anymore left. However, the tokenized data remain personal as long as the mapping exists in our separate service. And if we figure out that deletion in our tokenization system, then we're kind of good to go. So to understand how this works, let's see and dive into tokenization first and see how deletion works there too. To understand tokenization, I'm going to walk you through a scenario where we have a buyer named Human, and he has two favorite merchants, Allbirds and Gymshark. So Human buys 2 pairs of shoes from Allbirds and a pair of shorts from Gymshark. And his information could look like something like the left table before tokenization. So we have his email, we have the shop or the merchant that he purchased stuff from, and the product. And we're going to apply tokenization to this table one row at a time to see how it works. So we take the first row and we send it to our tokenization vault service. And because it has never seen this information before, it generates a new token, token 123, and sends it back. So this token gets persisted into the original table, and the original email or PII is gone. So next we do the same thing for the second row, and even though it's the same PII, the same data subject, it gets a new token, and that's because the controller is different. It's no longer Allbirds and it's Gymshark. Hence, we have token 456, and it gets replaced in this table. And for the last row, when it goes to the tokenization vault, because it's the same email, the same data subject, same PII, and the same controller, all birds again, it does not generate a new token. So it gives like the same original first token 1, 2, 3. So this is again that consistency property that I mentioned earlier. And if you look at this if you look at the tokenized version of this table, you can kind of see that how one data scientist can actually track a person without accessing the original email, because this token remains the same along the same controller. So now that we saw tokenization, let's see how does deletion work for tokenized data. So imagine this is how our tokenization vault looks like, and we're going to apply a bunch of scenarios, deletion scenarios, and see how it works. So for first scenario, imagine human has to be deleted from Gymshark. So all we need to do is set the data subject to human and the controller to Gymshark, and it will result in the 2 middle rows. So once we delete this mapping, essentially everywhere else these tokens 4, 5, 6, and 7, 8, 9 are persisted, they become random strings because they can never be detokenized back to the human@gmail.com. Similarly, human might ask to be deleted from all our merchants, and it will require to set the controller to a wildcard and the data subject to human, and it will result in the first 3 rows. So again, if it's this mapping is gone, all of those tokens become meaningless. And last but not least, it's also important for us to support our merchant purge. So, and what that means, in the event of a merchant wants to leave our platform, all we need to do is set the controller to the desired merchant and delete all of the mapping for all the personal information that is controlled by that merchant. And after that, essentially all the personal information is gone. So if you have noticed, in all of this deletion operation, we did not do a single thing or search anything in our data warehouse. And this is how tokenization allows us to efficiently, in fractions of seconds, perform deletions without impairing our analytical value, because tokens can be always exchanged for PII as long as they're not deleted. So in addition to all of this, another benefit of our tokenization system is that it allows for retention as well. So should we need to have this personal information gone after a certain amount of time without even having any privacy requests, we could introduce a retention policy on any of these rows. So putting all of this together, this is how our analytical platform looks like broadly these days. So again, events get fired from across the platform. They go through our messaging pipeline, and Scrubber tool uses schemas to apply pseudonymization, and if there's tokenization required, sends the PII to the tokenization vault, gets a token back, and rewrites the token back into the event, and the tokenized version of event gets persisted into our data warehouse. So are we good yet? Kind of yes and no. So we figured out how to delete stuff efficiently, but we face a lot of expected and unexpected challenges when we were going through these changes in our platform, and we think they are worthwhile to share. First thing for us was adoption, and it turns out having a sound solution versus adopting and rolling it out are 2 different problems. Initially, we struggled a lot with getting the approval and commitment from all of our stakeholders to roll out all of these new changes. And rightly so, because these are a lot of changes and kind of like an open heart surgery on our data analytics platform. So if you go and propose all of this to a person or to a team, probably the reaction you get is something along this line. In addition, all of this tooling that we built kind of solve our problem moving forward for the incoming data, but we were still sitting on years of historic data set that needed to be reprocessed. And while we don't have a perfect bulletproof solution for neither of these solutions, we learned a few lessons that might be useful to share. Proving the scalability and accuracy of our proposed tooling was very critical to build trust in our approach. We used the very same tooling and mechanism that data team uses to prove correctness and reconciliation of our tooling. This helped us a lot to bring confidence in our proposed changes. Another big factor in our success was making our tooling the default and easy option, or similarly, making the wrong thing the hard thing to do. And it turns out if you give people the right tool, everyone is eager to respect privacy and do the right thing. And last but not least, providing and respecting privacy doesn't necessarily mean to limit functionality. And in fact, quite the opposite. Most of our tooling brought new values to the table. And as an example, our obfuscator enriched data with high-level information that is very useful for our data scientists. And we introduced a lot of automatic integration between our scrub data sets and query engines and a lot of other routine tasks that data scientists needed to do. So there was a lot of encouragement and reason to use the scrub version of data as opposed to the raw PII value. For big effort of addressing historic data sets, we found that having organizational alignment was a very key factor. It facilitated to have a consistent messaging and help in broadcasting the importance of the work to the teams. And after that, it became a matter of working with team leads to find the right balance of completing their contribution versus not disrupting their team roadmap. We also found a dedicated task force helped significantly with regularly monitoring progress and pushing the needle forward consistently. Teams change, priorities change, people change, but having a dedicated task force helped the project to survive. And it is very important to have such a dedicated task force and move the needle forward, even so small. And last but not least, our goal was to reduce the amount of manual work to minimum by individual. To do so, we automated a lot of tedious work and introduced a lot of new tooling to do the manual labor with extensive documentation and technical support whenever it was needed. And all of these helped a lot and was very helpful in accelerating our progress. So we have been running these systems and tooling for about 2 years in production, and we handle something between 500,000 to 1 million events per second. Our tokenization vault holds more than 500 billion distinct PII or data points, and from which we do tens to hundreds of millions of data deletion per day. And we reprocess more than 100 distinct data sets on order of tens of petabytes of information worth of data. It took us about 3 years to develop, roll out, and reprocess our historic data. And more than 94 different individuals contributed to this project. So all of this to say that all of these techniques and tooling work actually in production and in the wild system. And it was a massive effort by a huge group of people. So in particular, we learned that unstructured data is evil, and it causes a lot of privacy, usability, and maintainability issues. We also saw how pseudonymization, in particular obfuscation and tokenization, can be helpful in tracking and handling of personal information in large databases. We also learned that solving technical challenges are not usually enough, and there remains organizational challenges to be addressed as well. Thanks for listening. There will be an extended version of this talk available under Shopify's engineering blog post with the same title. I'll be available for any question that you may have. Thank you.